Hello, my name is Melissa Kern, and I'm with Momentum Performance Materials, and I'm going to talk about a new silicone surfactant that provides improved foam properties in conventional foam. Momentum is a global company, and we also have a global technology presence. We have R&D centers in Cistersville, West Virginia, which is where I'm located, also in Leverkusen, Germany, and Shanghai, China. And we have ADE centers sort of peppered throughout the globe. And the work that I'm presenting here today was a collaborative effort of our global technology team. So some of the data was collected in Cistersville, West Virginia, but also some of the data that I will present today comes from our team in Leverkusen, headed up by Gabriel Kiss, and from SK10, who works out of Singapore. I'm going to start with a little brief background and what the objective of this work was. And like all projects, it began in a lab. So we have a little bit of the laboratory investigation to present today. And then out into the real world, we have some production data and industrial trials that we want to share. And then we'll close it out with some conclusions. So why are we talking about conventional foam, and what foam properties are we looking at improving? There are a lot of different applications for conventional foam, but one rapidly growing application is bed-in-a-box. And when we think of bed-in-a-box, we first think of things like visco foam or memory foam and the sort of specialty foam layers that really add value. But most of the bed-in-a-box mattresses have a base layer of conventional foam, and it's important that that conventional foam also meets the stringent requirements of foam that goes into a mattress in a box. So if we think about the bed-in-a-box value chain, we'll start at the end with the customer. And what a customer wants from a mattress is for it to provide a deep, restful sleep. And so the bed-in-a-box mattress maker does that with key features like temperature management and pressure point support, durability, low odor, a very consistent feel. And of course, when the mattress comes out of the box, the foam needs to recover completely. So in order to achieve all of those key features, the foam manufacturers have to meet increasingly stringent specifications that are trending towards higher airflow, improved property gradients, glass transition temperature control, improved mechanical properties, lower emissions, and all of that at a wider processing latitude. Now at Momentive, we are a surfactant, additives, and catalyst supplier, and we think about what can we do to help this? What can we do to help foam manufacturers meet these requirements and provide foam that ultimately ends up in a mattress that the consumer really achieves that deep, restful sleep? And in order to do that, we have to think about what is the role of the silicone surfactant and how do we choose a silicone surfactant for a specific application? So there are three key features that we look at from a silicone surfactant to provide. One is cell regulation, stabilization, and cell openness. Now, cell regulation is related to surfactant efficiency, but at the typical levels that are used in conventional foam, in typical use levels, we have a pretty broad latitude. So the cell structure is fairly well controlled over by most surfactants that are commonly used. And we don't have a lot of issues with improving cell structure. Of course, that can vary case to case on application, but in general. So we really look at stabilization and cell openness and, from the silicone surfactant. And stabilization is related to the surfactant efficiency and typically increases with surfactant use level. So properties that are indicative of good stabilization are improved property gradients, better side and top skins, higher bun heights, and all of that improves foam yield and gives a higher quality, more consistent foam. However, there is some sacrifice in cell openness to achieve that high stabilization. And cell openness is quantified by airflow. And again, there are increasingly higher airflow specifications because high airflow may impart improved compression sets and better foam breathability. But again, airflow decreases with surfactant use level. And as we try to achieve higher airflows, we may have to sacrifice stabilization and all of those benefits that we get from good stabilization. So when choosing a silicone surfactant, it really is looking at how to balance that stabilization and that cell openness for a given application. And the better that those two overlap, the wider your processing latitude. And so it's really key to find that overlap and optimize both of those properties for the best foam performance. So how do we go about achieving that optimization of stabilization and cell openness? If we think about a medium efficiency silicone surfactant in sort of a typical surfactant use level window, we look at foam height as some indication of stabilization. And as surfactant use level increases, we typically see an increase in foam height, and then it sort of levels off. Also, as surfactant use level increases, we see a steady decrease in airflow. And where the stabilization and the airflow are sort of optimized, that is our processing window where we can achieve the airflow that we need at a good stabilization. So if we take the surfactant and we try to increase stabilization by using, say, a high efficiency silicone surfactant, if we see that increase in stabilization, but again, that sacrifices airflow, and that may also change the slope of this airflow curve so that we see a more dramatic drop in airflow as we increase surfactant use level. And we achieve the benefits of high stabilization, but by getting that lower airflow and sort of changing the slope of that airflow line, we narrow the processing window where we get a good overlap of good stabilization at airflows that meet specifications. We take that same surfactant and go in the different direction and try to make it more open or increase the airflow. We see some sacrifice in stabilization. And so this may, by sacrificing that stabilization, it may lead to densification, and that's what impacts the property gradient, so the density from top to bottom and the hardness from top to bottom. So we lose that improved foam yield that we expect from good stabilization when increasing the airflow to meet the airflow specifications. So if we think about what is the ideal balance of these two, of stabilization and cell openness, what does that look like? What would we like it to look like? And really, it is a way to balance the airflow, so to increase the airflow without sacrificing stabilization. And not only to increase the airflow, but to change the slope of that curve. So if we can have a less dramatic drop in airflow with surfactant use level, we can effectively broaden that processing window. So we would like to increase the airflow with a broader processing window without sacrificing those properties that are indicative of good stabilization, such as our property gradients and top and side skins and overall foam yield. And so this is really what we set out to achieve with this work. How can we push our silicone surfactants to this sort of optimal balance of stabilization and cell openness? And we did our development work in the lab, and we came up with, now it's called Nyack Silicone L894. And we looked at it in a variety of different foam formulations at different densities of conventional foam. And we compared it to a variety of different surfactants, both medium efficiency and high efficiency. And as I mentioned, this was a global effort. And so some of the work was done in West Virginia, but also in Germany and Singapore. And so the surfactants that were compared to L894 were the surfactants that are common in those specific regions. We began at a low density formulation, so 16 kgs or about 1 pound. And this is a methylene chloride was used as a blowing agent. And we compare the surfactants at 1 part. Now in the lab, we look at foam height and the relative foam height of the surfactants as an indication of relative stabilization. So we can see that L894 has a foam height better than the two medium efficiency surfactants that were evaluated, and less than the high efficiency surfactants. And so this is what we expect. we wanted improvement in stabilization based off of a typical medium efficiency surfactant. And you can see that we also had the highest airflow of all the surfactants when using L894. So we take the same formulation and we change the use levels. We always start at a low use level, the sort of outside the typical use level range for that density. And when we strain the surfactant that way, we can really differentiate between the efficiency of the surfactants. And so again, we see the L894 is in between, has a foam height in between that of the high efficiency silicone surfactant and the medium efficiency silicone surfactant. I mean, we see that trend consistently as we increase the use level. And what we also see when we look at airflow is that Nyack silicone L894 had the highest airflow at all use levels. And so this is really what we wanted to see. This is what we were aiming towards, having an efficiency between that of medium and high efficiency, but having that high airflow or better cell opening. So if we go up in density to a 24 kg foam, and this is about 1.5 pounds, we compared L894 to 3 medium efficiency surfactants and 1 high efficiency surfactant. And so there are 2 use levels, 1 part and 1.3 parts. And again, we can see that L894 had foam heights that were higher than the other medium efficiency surfactants. And when we look at the airflow, we see that at both use levels, the airflow was higher for L894 compared to all of the other surfactants that were evaluated. And we also see we don't see a very large decrease in airflow when we increase the use level from 1 part to 3 parts. As we go into an even denser foam, so now we're at 32 kgs or about 2 pounds. When we go up in density in conventional foam, then we see less differentiation between the foam heights or the efficiency of the surfactants. And that's because with higher densities, we don't need as much stabilizing power as we do at the lower density. But where we do see advantage with L894 is in the airflow. So most of the other surfactants that were evaluated had a dramatic decrease in airflow when going from 8 parts to 1.1 parts. But we did not observe that with L894. And so again, this indicates a better processing latitude as relates to airflow when using L894. The final laboratory investigation was completed in Singapore, and this was ahead of one of the industrial trials that I'll talk about a little bit later. So it was a new bed-in-a-box formulation that was in development at that specific site, comparing L894 to a medium efficiency surfactant G. And the use level was increased from 1.1 to 1.5. And what we can see is that the foam heights between the 2 surfactants were very similar, but the airflow for L894 was much higher than that for surfactant G. To wrap up the laboratory investigation, what we wanted to achieve with L894 was really an efficiency better than the typical medium efficiency surfactant, but with an improved airflow. And so we did see that. We did see higher airflows like this dotted line for L894, and an efficiency in between that of the medium and high efficiency surfactants. And this performance was consistent across geographic region and across foam formulation and foam density. So with these satisfactory results, right, we wanted to see how L894 looked in industrial trials. We have 6 industrial trials that we're going to show today, and again in different formulations using different machines. Compared to the all medium efficiency surfactants that were sort of incumbent for those formulations at that specific site. So we'll begin with, again, a low density formulation, so 15 kgs, just shy of 1 pound. And this was done on a high pressure continuous CO2 compared to a medium efficiency surfactant. And what we can see here, when we were in this trial, we really wanted to look at the property gradients And we can see that when using Nyack silicone L894 compared to surfactant E, we see an improved density gradient from the top of the foam to the bottom of the foam. So the incumbent surfactant E was about 8.6% gradient, and L894 was less than 3.5% gradient. And when we go to the hardness gradient, we see an even more dramatic improvement when using L894. So the percent gradient for the incumbent surfactant E was over 16%, and L894 was just over 4%. So there's a 75% improvement in hardness gradient. And this data was 3 months of production data of both L894 and surfactant E. On the same machine, still a low density formulation at just shy of a pound, L894 was evaluated in a hypersoft formulation, again compared to a medium efficiency surfactant E. And again, we see these same improvements in density gradients and hardness gradients when comparing L894 to surfactant E. So we see an improvement from 3.3% to 2.3% in density gradients, and again in the hardness gradient we see an even more dramatic improvement from over 18% to just about 10%. On the same machine at the same site, L894 was also evaluated in 2 higher or medium density type formulations, so 25 kgs, about 1.5 pounds, and 35 kgs, just a little bit over 2 pounds. Again, we see these very tight gradients of properties, and these tight property gradients, both density and hardness, are indicative of strong stabilization that L894 provides. So we have, so now we're moving geographic regions, and this data is from Southeast Asia. And so it's a low density formulation, again, just shy of 1 pound, and methylene chloride was used as the blowing agent. And L894 was compared to surfactant G, another medium efficiency surfactant. And in that comparison, we saw that L894 gave a higher airflow when all of the properties, all of the other foam properties were very similar. And at that same site, on that same machine, L894 was evaluated in a bed-in-a-box formulation. So this was the work that the last laboratory data was ahead of. So this was a bed-in-a-box formulation that was in development, and L894 was being evaluated against surfactant that was already used at that site, surfactant G. And again, L894 provided a higher airflow and a reported improvement in side skins. And so that's, again, indicative of better stabilization. The final set of industrial data are some medium to high density foam at 30 kgs and 40 kgs. That's just shy of 2 pounds and almost 2.5 pounds. And this target application was bra cups, and bra cup foam also needs to have very good compression sets because the foam is shaped at high temperature and pressure, and so it needs to recover from that. And L894 was compared to another medium efficiency surfactant, surfactant H. And again, at both densities, L894 provided higher airflows than surfactant H, and this led to improved compression sets. And all of the other foam properties were similar between the two surfactants. In conclusion, we want to go back to, did we achieve this more optimal overlap of stabilization and cell openness? So we looked at L894 from the stabilization perspective. In the labs, we had foam heights that were consistently better than those of the medium efficiency surfactants that we evaluated. And when we took that into industrial trials, we saw better property gradients in some of the trials. We saw improved top skins and side skins. we saw bun heights very similar to the other medium efficiency surfactants that were evaluated. And these results were consistent across all of the industrial trials, which were conducted in different geographic locations, using different source materials and in various foam densities. And when we go to cell openness, again, in the lab trials, L894 had the highest airflow in every formulation that it was evaluated in compared to every other surfactant that it was evaluated against. And we also often saw the lowest decrease in airflow with increase in use level. Again, an indication that with respect to airflow, there's an improved processing latitude with L894. And when we went to industrial trials, L894 consistently provided a higher airflow compared to the surfactants that it was evaluated against, the other medium efficiency surfactants. So we believe the L894 really does optimize that overlap of stabilization and cell openness and can provide optimal foam properties at a very good processing window. And with that, I would like to thank my co-authors, Gabriel Kiss and SK10, and the Momentive North America PU Lab team. Our fearless leader is Susan Norris, account manager Kevin Myers, and then our technical team, Jolene, Tiffany, and Kyle. And with that, I will say thank you for listening, and I'll be happy to take any questions whenever we have an opportunity to speak.